Okay, I'm very happy to introduce Christiane Schmidt today, who will be giving a talk. She's at Linköping University, and I just checked to verify my memory. She has given a talk in the seminar several times in the past, and we are happy to have her tell us about her more recent work now, so I'll just let her speak.
Thanks for the introduction and inviting me again. So I think it has been 8 years or something when I last talked. So today we'll look at k-transmitter Watchman routes and some guarding problems. And I have to admit, I was a bit optimistic when I announced the title. So we'll look at one guarding problem in addition to that. So looking at the agenda, which I hope you see the new slide. Perfect, that worked. So first, I'll introduce you to k-transmitters. So what are these? Then we'll look a bit at the Watchman route problem, and then we'll see how we combine that and what we were able to show there. And I decided to go into a bit more details in the proof there. And so then I'll only look at one guarding problem and mainly at an open problem at k-transmitters, which Joe will be very aware of. And then I'll give a bit of an outlook. So I'm very sure you all are aware of the AppGuard problem, so I'll give a very brief hint to that. So we have a polygon and we want to know how many guards do we need to monitor it. And then, of course, we have usually the visibility polygon. So that's all the points in the polygon for which the line segment from our guard to the point are contained in the polygon. So that's the normal thing that we want to do. And then here, well, we would need another guard, and we can also give a lower bound that we need as many. What we'll do for k-transmitters is we will alter some part of the AppGuard problem. So usually what we can alter is either the capabilities of the guard or the environment that we want to guard. And here we'll alter the capabilities of the guard. So if this guard was a 2 transmitter, then he could actually see this violet point. Why? Because the line segment hits the polygon in 2 connected components, or we're intersecting the boundary twice. We're looking through 2 walls. So that could be seen by a 2 transmitter. And so if this is our polygon, then actually a single 2 transmitter could see the entire polygon, while our normal guards could not. And if we try to formalize that, then again, we look at the line segment between a guard and another point. And if that intersects our polygon in at most 2 connected components, or for a k-transmitter in at most k connected component, then the 2 points can see each other. And then in the same way that for a normal guard, or this human vision that we usually look at, can define a visibility polygon, we can define a 2 visibility region or a k visibility region as a set of points that a point 2 sees or k sees. And then if we would have stationary guards, then in the same way that we have a guarding set, we have a 2 transmitter cover, so a set of 2 transmitters that covers our polygon if the union of the 2 visibility regions of these points completely cover the polygon. And in the same way, we have a k-transmitter cover. So really the main thing is we can see through k walls, or we can see through 2 walls, instead of having this mimicking human vision where we really can't see around corners or can't see through walls.
Christiane,
yeah.
Just a quick question. So you're restricting the target to be in the polygon, but under k-transmitter, you could also see some of the domain outside.
Exactly.
But,
we could also
but right
see
now
some
you're restricting to P.
We're restricting to P, and that also means that essentially only even values of K are really interesting, but we could also place outside and look at odd values, or even look outside from inside. So yeah, we could do all of that, but usually here we just want to see the polygon. And so the first note that makes this very different from normal guards is that the visibility region of a 2 transmitter can have order n, or at most n, in fact, connected components. So everything that is shaded in maybe orange, we can visit any of the points and we will 2C the point P. And so that's already holds for a 2 transmitter. It also holds for a k transmitter. So it's not that we have one connected visibility polygon for each point in the polygon. So let's look a bit at what people looked at for k transmitters. So the first kind of obvious thing were art gallery theorems, so these kind of upper and lower bounds, so and so many guards are always sufficient and sometimes necessary for a class of polygons. And so Eichhorst et al. Looked at monotone orthogonal polygons and got, for example, n-2 over 2k plus 3 rounded up many k transmitters for monotone n-gons. And so they have tight bounds for monotone orthogonal ones. And then Ballinger and al., they did not restrict to polygons, so that kind of fits with Joe's questions. So they just looked at line segments in the plane and they wanted to monitor the complete plane and then gave, again, upper and lower bounds for the number of guards that are necessary for that. But they also looked at simple n-gons, and they provided a lower bound there of n over 6 rounded down many 2 transmitters. So there exist simple polygons for which you need n over 6 rounded down many 2 transmitters. And then in 2018, we looked at, some slightly extended 2 transmitters. So we didn't only look at point transmitters, but also edge 2 transmitters. And there we gave bounds for simple polygons for monotone, polygons for orthogonal ones, and for orthogonal monotone ones. And what we also did, and which is maybe more interesting here, we improved the lower bound from Ballinger et al. To n over 5. And so if you look at the construction on the right, you have this kind of witness A, and in its visible region, which is shaded in gray, you have 5 vertices. And then if you make sure that the rest of the polygon is really below these 2 lines, you have a lot of these sketches around the central part of a polygon, then you get a lower bound of n over 5. And then, well, these are kind of all the known art gallery theorem results. And then, of course, the other usual question that we have is, well, given a specific polygon, can we compute the minimum 2 or k transmitter cover? And there we have a couple of hardness results for point 2 transmitters, for point k transmitters, and for edge 2 transmitters in simple polygons. And one of them is even for orthogonal polygons, which is not that surprising because we know that the art gallery problem is hardness. So what else have people looked at? A slightly more extended version are sliding k transmitters. So what's a sliding k transmitter? You have a line segment in the polygon, could be an edge, but also could just be something that you place in the line segment that you place inside the polygon. And then what the sliding k transmitter sees is not the weak visibility polygon or something of that segment, but you look at everything that you 2 or k see orthogonally to that line segment. So here, if this red line segment would be a sliding 4 transmitter, then what is shaded in red is what it could see. And there, people have looked at 2 different objectives, either placing the minimum number of these sliding k transmitters or the minimum length of all these line segments. And for both versions, so for Medavi et al. Looked at minimizing the total length of the sliding k transmitter that they placed. And they showed hardness for k equals 2 and gave a 2 approximation for constant k. And then Biedel et al. Looked at minimizing the number of sliding k transmitter. And again, they gave a hardness result, in this case for orthogonal polygons with holes, but already for zero transmitters, and they have a constant factor approximation. And then the last thing that people have looked at were k-transmitters, which maybe seems a bit strange that that's the last thing, but that was the computation of the k-visibility region, so the set of points that a k-transmitter can see. And so two groups of authors with Evgeny Behu as a first author, they first did the computation in a limited workspace model in 2019, and then an order in K algorithm in general. Okay, so this is kind of the setup that we have for k-transmitters, mostly stationary or limited to either an edge or a line segment that we place somewhere in the polygon. So before we go to the complete topic of the talk, we'll briefly take a look at the Watchman problem, because what we want to do is we want to use a k-transmitter as a watchman. So let's take a very brief look at the Watchman route problem as well. So far we had stationary guards. Now we have one guard, the watchman that can move. And so if we have a polygon, then we want to find the shortest tour in the polygon along which this watchman can move, and while doing so, actually sees all the points. So something like this pink structure would be a watchman route. So even there, we look at computing the optimal tour, and while guarding with k-transmitters is hard already in simple polygons, here we have that can be computed in polytime, either if we're given a starting point on the boundary, or even in the case without a starting point. And then if we go to polygons with holes, then the Watchman problem also becomes hard. There's a very important structure that all these results use, and that whenever we think about Watchman problem, well, we probably have that in our mind, and that's extension. So what is an extension? Well, we look at a polygon and we have a cut, so we extend an edge, like here, the edge C1 or the cut C1 that defines two subpolygons, and in one of them, if we're given a starting point, the starting point will be contained. And then if we have two cuts, we can define a domination property. So in this case, the cut C1 will dominate C2. What does that mean? Well, if we start at S and visit cut C1, we automatically also visit cut C2. So C1, visiting C1 is enough, and we'll also have visited C2. And then if we have non-dominated cuts, these are essential cuts, they are not dominated by any other cut. And so if we want to solve a Watchman route problem for a normal guard, then we know that we have to visit all of these essential cuts. And this property, as we will see, unfortunately, does not translate to our k-transmitter Watchman routes. So what I focus on is a result that Ben Nielsen and I obtained, and that will appear at Welcome 2023. You can find it on arXiv already. So now we look at trying to compute a Watchman route with a k-transmitter. So what do we have? We have a mobile k-transmitter, and what you can think about is that we have lots of points in our polygon to which they send out some data. So we can get the data to a certain number of walls, but then at some point not. So we want to drive around and collect this data. And so this could either be a discrete subset of points somewhere in the polygon, or of course the complete polygon that we want to see or KC. And so we want to find the shortest tour for a k-transmitter that sees all of these points in S or the complete polygon, and it should move within the polygon. And so again, it's in the same way as for the general Watchman route problem, we can look at this problem with a given starting point somewhere in the polygon, possibly in the boundary, but maybe also somewhere else in the polygon, or for the case without a given starting point. And So again, the most important part here is that unfortunately our extension that we have when we look at normal guards or zero transmitters, they don't really translate. So as we saw before, we know that for a single point, the visibility region or the two visibility region is disconnected, can have order n connected components. So what does that mean? Well, to see this one point, we could visit either of these regions. And if we now look at what an essential cut is, that is defined by the extension of an edge of our polygon. However, if we would slide a point along an edge, then this 2 or k visibility region can alter completely. So it's really not anymore a local structure, and it also is not a structure that is defined for a complete edge. So different points you can see from different parts of the polygon. So we'll have to, well, what we would like to do is to find a similar structure. We don't have that, so we'll make use of some other properties to still find an approximation. So another observation is that, so if you think that the gray is our polygon, and now let's make it a tour in pink, so we'll go back and forth. Then if you look at these 4 points in pink, from these you can actually see the entire boundary highlighted in red in the central rectangle. But there is no point along this tour from which you can see the turquoise point. So if you see the entire boundary for a 2 transmitter in a simple polygon, this will not be enough to also see the complete polygon. So that's kind of an analog of if we would have guards and not a watchman in a simple polygon, and then having the Gottfried's favorite polygon where we could also see the boundary but not the interior. Here we can get that even for a watchman, because yeah, looking through edges, we can somehow mimic the holes for that case. So the first thing that we can show is that even if we have only a discrete set of points S, and we don't have a starting point, then we will not be able to get a polynomial time approximation algorithm with approximation ratio constant times ln S, where S is the cardinality of our discrete point set. And that already holds for k equals 2. So we can't approximate to within a logarithmic factor. And the reduction here is from Sadker. So what do? Let's say we have a Sadker instance, so our universe U and a collection of sets C. We build the bipartite graph on this instance, and then we transfer that into this kind of polygon. So what does that mean? We have all our sets in C, they are at the end of, or at the tips of spikes. And these spikes are connected to a spiral structure, and we add to our set U, the point in the interior of this spiral structure, which we call B. And so all our points that represent our universe U, plus this one point in the spiral there, these are the discrete, or this is the discrete point set to which we need to establish a connection. And so what do we know? Well, we know that the 2 visibility region of that point in the interior of the spiral really is contained in that spiral. So we need to visit the spiral. And where do we place all our points in U? They're in this bottom box, and only the edges of our bipartite graph, they, through these you could see into the bottom box. Otherwise we have these T structures that mean that anything else from the yellow points to the green points is really not possible. You can't see down there. And then what we do is we have a very long corridor on the right-hand side. And at the bottom there, it's really just epsilon. So if you happen to be at the bottom, then you can see all the green points. So why are we essentially done with that? Well, we know that we have to visit the visibility region of our point V, and then we can't afford to go down this very long corridor at the side. So we really need to find the right subset of the spikes that we need to visit to also see all of our green points at the bottom. And with that, we also get the case for a starting point, because then we just pick a starting point somewhere in this pink visibility region of our point S, and then we have the same kind of reduction. So when we have a discrete set of points, and either for a starting point or without a starting point, we can't approximate better than a logarithmic factor. And so what we obviously want to obtain then is some approximation algorithm that comes close to that bound. So we don't come exactly close, but we have a couple of more logarithmic factors in there. So we have a simple n-gon, and if we, with an approximation algorithm that I'll tell you about in a moment, we compute a route R, and that is within a factor of log squared Sn, log Sn, log S of optimum. So let's see how we get there. So what we do is we create candidate points for each connected component of a K visibility region of all of the points in S. So the points in S, when we look at the K visibility region, that can have many connected components. For each of them, we want to have a candidate, and some want to argue that we pick good candidates so that we can work with them. So what are they? The candidate points are the intersection of geodesics from our starting point with a cut. What's the cut? So here we have our point S1 that has, in this case, 2 connected components. And if we're given a starting point, then the cut is the window of that connected component, such that whenever we have a path from S to a point in the connected component, we need to cross this window. So if we look at a slightly larger example, so here we have our starting point S in white, and we have our set S contains 3 points, S1, S2, and S3. So S1 is in blue, S2 is in red, S3 is in green. And so, for example, the 2 visibility region of S3 has 3 connected components. They're kind of all at the bottom there. And in turquoise, you see the cuts. So what's that? Well, if we want to go from S to any point in these connected components, we need to first cross these cuts. And so what did we want to do? We want to compute the geodesics from S to all of these cuts. And at the intersection point, those are our candidate points. And we actually have a slightly richer set of candidates. We have on each of these cuts one more, the light pink points that are just a general representative of these cuts. So just thinking, well, somehow we visited this cut. And what do we do? On the pink points, we build a complete graph. And so these are the light gray edges, and the length is always the geodesic between the 2 pink points and S that you're looking at. And we add some pink edges, and they get cost 0, and they are always between a pink point, which we call Pij, and one of these light pink ones. So what's the idea there? Essentially, well, if you visit a certain cut, you get at least that cut and maybe also some other cut that you crossed for free. So let's look at an example. If from S, we visit this cut of K33 to the left, then we get the cut to K15 and the one to K21 for free. So we add edges in the graph of length 0, so the ones highlighted in white there. what else do we know? We know that our graph has order n times s many vertices. And now we group our points. So we have all these candidate points, the dark pink and the light pink ones, and all the points that belong to a specific point in S, we group them. So if you look at the right-hand side, we have kind of grouped them in blue, red, and so on. So what does that mean? Well, we have to add one more group before we get further. We add a group gamma 0. That's just the starting point S, because we also want to visit it. So again, here, gamma 1 are all the candidate points that belong to S1, so that lie on some cut of a k-visibility region of our point S1. And so in red, we have all those that belong to S2, in green, those that belong to S3, and then in, well, royal blue, I guess, we have S. Okay, so why do we do that? Because what we want to use is a group Steiner tree problem. So let's look again what that is. We have a graph with m vertices and q vertex subsets groups. So each vertex belongs to one of our groups. And then what we want to find is a minimum cost subtree of the graph that contains at least one vertex per group and that minimizes the weight of the tree. And for that problem, Gerk et al. Gave an approximation algorithm with, well, this approximation ratio order log square m log m log q. So what do we want to do? We compute a group Steiner tree with our groups on our created graph. In our case, we have m is order n times s, and q is s plus 1. Well, we have all the groups for each point in S, plus a one group that contains the starting point. And what do? We compute this approximation to the group Steiner tree, we double that tree, and then we have a route, and we know that this one is going to be feasible because we visit 1 point per group. So we make sure that we visit the k-visibility region of each of our discrete, each point in our discrete point set at least once. So the thing that we still need to do is why this thing will also give us the claimed approximation factor. So we know it's feasible. We will visit all our, we will see all our points in S. We only need to figure out why this also gives us the approximation factor. So what's the idea? What we think about is we look at the optimal route, which we don't know, but we want to alter it so that it actually passes through the vertices of our graph. And want to say that by altering like that, we only increase the total length to a constant times the optimum. So we don't get too bad with that. So how do we do that? Well, first of all, we're not really interested in all the cuts anymore, but only in the ones that the optimum actually visits. So all the cuts of all our k-visibility region of the connected components that op visit, they are in the set C. And then we look at, so to have a point to compare to, the point at which we visit the cut Cij to the j's connected component of our point as I for the first time, or j, that's where optimum visits this cut for the first time. Then we'll filter a bit more from our cuts. So we're not interested in all the cuts that the optimum visits, but only in the essential cuts of those. So again, the remainder essential cuts were the ones that were not dominated in any other way. So if we cross the other cuts, if we reach these essential cuts, we will always cross the other cuts as well. And then we keep on filtering out our cuts a bit more. So now we order our cuts by the length of the geodesics to these cuts. So we have the longest one first, and then the next cut is the one with the second longest geodesic. And what we want to do is we have our current geodesic, so we iterate over from longest to shortest. We look at our geodesic and look at all the cuts, all the eccentric cuts that this geodesic intersects. And we are going to throw all these cuts away. So in the end, we only have, starting from the longest one, these cuts left to which a geodesic does not cross any of the other cuts in the set that we are left with. And so this is the cut set C double prime. Okay, so what do we do then? Well, the first claim that we have is that these are actually a set of independent geodesics. So no essential cut that we have is visited by two of these geodesics that we're left with. And we also say that each essential cut that's visited by the optimum is touched by exactly one of the geodesics. So no two of the geodesic that to the cuts that we're left will visit any of the cut visited by the optimum. And so what we'll do is, okay, look at all the geodesics where they hit our cuts that we're left with. This will be in the same type of points as those that we identified as vertices of our graph, because it's an intersection of a geodesic with a cut. And so we put all of these points into a set. Okay, so what do we do then? We build the relative convex hull of all the points where the optimum visits our essential cuts, and those points Pij where the left out cuts intersect their geodesic. What do we do with that? So now we look at if we have a point where the optimum visits a cut and a point where the geodesics intersect this cut, then we can show that the relative convex hull will not be intersected by any other geodesic between these 2 points. And so if we look at 2 consecutive points on this relative convex hull of the optimum, there can only be at most 2 points of our points that represent points in the graph, so these points in PC double prime. And what we can also show is that we can alter our optimum to visit all of the points in the this relative convex hull, and we increase the length by at most a factor of 3. Then we have the relatively easy observation that if we only have the relative convex hull of the points that are represented in our graph, then that's not longer than the relative convex hull that also visits the points of our optimum. And we know that we visit 1 point in each of our group, so we actually have a route as the one that we wanted to compute in our graph. And so if we put all of that together, we might need to add a factor of op to connect to our starting point. But what we have is that the length of our route is at most a constant time this logarithmic factor away from the optimum within the graph. The optimum within the graph is at most a constant away from this relative convex hull of the points that represent points in the graph in our polygon. That's at most a constant away to the relative convex hull if we also throw in the points at the optimum visits. And that is at most a constant away from the optimum that is within our polygon. So these are a few too many steps. So if you have any questions right now before we go into the claims, is there anything that I should maybe explain again? No? Okay, so we have these 4 claims, and these we still have to show to really get to our approximation ratio. The first two are quite easy, so these will get out of the way very fast. So what did that say? We have an independent set of geodesics that we get directly from the way that we filtered, because we ordered them by decreasing lengths, the cuts by decreasing lengths of the geodesics to these cuts. Then we iterate of them in decreasing order, and we say, well, if the current geodesic that we look at intersect some other cut, well, we throw these away and alter the geodesics to them. So we make sure that no two remaining geodesics visit the same cut. So they have to be a set of independent geodesics. The next claim that we have is that if each essential cut that's visited by the optimum is touched by exactly one of the geodesics that we're left with. Why is that the case? Again, we know that the geodesics that we start with visit all the essential cuts. And what do we do then? Well, we only delete a geodesic if that's already visited by a longer geodesic. So we already know that this cut will also be visited. So we can throw away that geodesic. And in the end, we visit all of them, and it will be only one because we filtered out all the other ones. Okay, so what else did we want to say? So we wanted to have this relative convex hull. So again, why do we want that? Because we want to reroute the optimum to also go via the points in our graph. And we want to make a statement of what can actually happen. So how long can that be? And the first claim then is that if we look at this relative convex hull and we're a point of the optimum and a point that represents a point in our graph on the same cut line, then there can't be a geodesic that intersects in between. And so we need a couple of lemmas to show that. So we really, let's say we have a cut of a specific connected component of the K visibility region of our point Si. And now we're looking at the point Oj from the optimum and our point Pij, both of them on the relative convex hull. And now we say there can't be another geodesic intersecting that. Why? Well, let's assume there is one too. Another cut C prime that intersects between our points Oj and Pij. And then this will intersect our cut in some point. Let's say that this is PC. Well, what do we know? If now the geodesic to this other cut C prime is longer than the geodesic to our cut, we would have deleted the geodesic to C in our filtering thing. So C wouldn't at all be something that we consider. If, on the other hand, the geodesic to C prime is shorter, well, then we can just restrict that to the part until we hit our cut, and we would have something that's shorter than what we would claim is the geodesic. So that can't happen. If they happen to have the same lengths, well, then it depends a bit if they intersect in one point. Not going to go into details, but essentially either we filtered out the geodesic to that one, or we get a contradiction to what we have being a geodesic at all. So we showed this first statement. Now we want to go further here. So what do we show? If we have 2 points of the optimum on this relative convex hull, then in between we can have at most 2 points that lie in our graph. And so let's say we have these 2 consecutive points, and we know from what we just showed that the point on the same cut can lie in between. So let's say we have points Oj, Pij on one cut, and Oi prime and Pi, well, I prime J prime and Pi prime J prime on another one. And now we want to have a point in between on the relative convex hull. So this is the middle pain point there, P kappa lambda. What can we say? Well, optimum also has to visit that cut. And because we visit OIJ and OI prime J prime consecutively, well, we either have to visit it before or after these points. Well, let's say we do it after, as we have in the figure. Well, we know that the cut on which these 2 points lie is a line segment. So if we look at this red polygon there that we define, then we know that one of our points of the graph has to be inside of that polygon, so it can't be on the relative convex hull. So we really know if we have 2 points of the optimum on the relative convex hull, we can have at most 2 of the points from our graph in between those. So now we only have to show this part of, hey, you can actually also include the points of our graph, and you will only increase the optimum by a factor of 3. So why do we do that? Well, what did we learn? We can have at most 2 points of our points in the graph and between the points of the optimum. We know to which cuts the geodesics that go to these points, and that means we also know that the geodesic, for example, the Pij, has to intersect the optimum, so that there's an intersection in this point rho ij. What do we know? Pij, the pink point, is where the geodesic intersects. So if we go from this intersection point rho ij to Pij, that will always be shorter than going from rho ij to another point Oj on the same cut. And what we do is we reroute. So normally up would go from Oj to Oi prime J prime. So from one blue point to another blue point. How do we rewrite? We go from blue to yellow to pink to yellow to the other yellow point, pink, yellow, and blue. And because our pinks points are intersection point with geodesics, so we have this inequalities from the yellow points, we increase the total length by at most a factor 3. What do we know? This new tour that we have there that will visit all the points that we have on the relative convex hull, well, then, of course, we know that this is, from the inequalities again, at most 3 times the opt. And our relative convex hull is the shortest one that visits all these points. So we also get the factor 3. So we now rerouted our optimum to go through the vertices of our graph, and we increased the length by at most a factor of 3. So the last thing that we have to show is that now, instead of really also visiting all the points of the optimum, just visiting the points that represent our graph, this won't be longer, and we do visit at least 1 point per k visibility region of each point in our discrete point set. Well, the first statement is really easy, right? Because, well, we have a subset there. So if the convex hull of a subset is at most as long as the convex hull of the superset. So that one we get kind of for free. So the next thing that we want to say is that all the points that are intersection of geodesics and cuts, 2 cuts that we're left with after all our filtering, all of these have to be on the relative convex hull. So none of them can be in the interior. Why is that the case? Well, assume that we have a point that's not on the convex hull. What do we know? Well, by our first claim, because we ordered them, there will be no geodesic that intersects the cut of that. So what else do we know? Well, a cut always connects to boundary points. So like here, this cut Cij connects a point X and Y, and our point Pij has to be somewhere on that cut. By that definition, we know that the convex hull has to be contained in this polygon PSCij, so the polygon in which the cut split that also contains our starting point. so it doesn't cross this cut, well, then also the point that's on the cut has to be on the relative convex hull. And so then the last thing is we need to show that we visit all the cuts that we started with. Which one do we have? C are all the ones visited by opt. Then we look at the C prime, those are the essential cuts. C double primes are those that are visited by independent geodesics. And we can actually split that up into 3 parts and can show that we visit all of them. Why? Those that are essential, those that are cuts but not essential, they are dominated by the essential cuts. So we will definitely visit them. If we visit all the cuts, all the essential cuts, we will visit all the non-essential cuts. All the cuts in C double prime, so those that have independent geodesics, we showed in a lemma before that we will visit them. So those that we are left with are the ones that are essential, but that don't have our independent geodesics reaching them. So let's say we have a cut in there, and that is not visited by our relative convex hull. So let's say that's our cut C. We know that this one can't be one where an independent geodesics hits it. So why? What does that mean? We filtered it out at some point. So there has to be a longer geodesic to another cut that crossed our cut C. And so we say it's one that goes to cut Cij. What do we know? Well, any tour that visits our starting point and the point in which the longer geodesic hits its cut has to intersect our cut. And we know that the relative convex hull is such a tour. We just showed that in the previous lemma. So we also need to visit these cuts. So what we can show is we visit the relative convex hull of the points representing points in a graph will visit all the cuts that the optimum visits. And so then the last one that's quite easy is that we will visit one point in each gamma I, possibly except for our starting point. Why is that? Well, the optimum is obviously feasible. That means that the set C of all the cuts that the optimum visits has to visit at least one cut from each group. Well, if that's the case, we know that our relative convex hull visits all these cuts C, and with that, it also has to visit at least one cut in each group. And so with that, we also showed all our claims. So what we really did say is we can reroute the optimum through graph, 2 points that represent points in our graph, and we only increase it by constant by doing so. So putting that together with the approximation ratio that we get from the group Steiner tree and the size of our graph then gives us the approximation ratio of this log square Sn log Sn log S. So of course there is still a gap. So the lower bound that we get from the set cover reduction is ln of cardinality S. And here we also have the size of the polygon in the approximation ratio. So we have log square Sn. And so it's and also obviously more logarithmic factors than in the lower bound. So there's still some gap to close, but at least we have some polylogarithmic approximation there as well. So I promised a bit about some problem, or looking at some guarding problem actually, before we go into making an outlook for the k-transmitter Watchman route. So when you looked at this thing, we have the lower bound of n/5, and the best upper bound is still the n/3 that we get from normal visibility. And so at some point we were able to eat up an ear, so we have an n-1/3, which is not exactly great. And it's really not using that we have these very stronger capabilities, right? So if you, for example, look at this polygon, a single two transmitter covers it. For 0 transmitters, we need 3. And so we still have that gap. And there was also Joe, who's here, who highlighted that already in 2012, that really the upper bound is only coming from 0 transmitters. There seems to be some nice property. So if we have a 5-gon, every 5-gon can be covered by a single two transmitter placed anywhere within the polygon. And we also have the statement that if you have a 6-gon, pick any edge, then, well, either one of the endpoints or the other, this will definitely cover the 6-gon. Problem is, if we look at a larger polygon, it can look like that. So yes, the yellow thing is a 6-gon, but you have these interlacing from other parts of the polygon. So there's really no 2 transmitter that can see this complete 6-gon. So whenever you want to come up with better bounds, you really have to make sure that you're not using any local properties. So we're currently trying to make progress towards a sub-problem of that. So we're kind of hopeful to that. But for the general one, where we really want to cover the complete simple polygon with 2 transmitters or k-transmitters, but 2 transmitters for starters. Joe's claim from 10 years ago is still pretty much the same. So as I said, we're at n-1/3 at the moment, which is a bit frustrating, I would say. And so that is in a way also connected to what I have in my outlook, because what we did here is really only for a discrete subset of points. And why is that? Because we have no structural analog to what extensions are for 0 transmitters. So here we make sure that, okay, we have a single point, and then we kind of have extensions again, because that's all the cuts of the connected components of our k-visibility region. But if we don't have a discrete subset of points, then we really need some kind of analog. So any claim what we need to visit to have a tour. So the question is really, can we get a good approximation factor for the case where we want to monitor the complete polygon with a 2 transmitter or a k-transmitter, be it with or without a given starting point, doesn't really matter. So I think there we really need some kind of extension to be able to do that. And then again, the other thing would be to improve these combinatorial bounds. Yeah, we hope we're in the way of making some progress, but not really there yet. And with that, I would say thanks for your attention, and I'm happy to answer questions.